Section 7.4, how to write a balanced chemical equation. So here are the instructions, and then we'll go through and do some examples, and hopefully it'll be clearer. First, you write a skeletal equation. You just figure out what the correct formulas are, and you write those down for the reactants and the products, and you put an arrow in between. And you may need to review Chapter 5 for nomenclature, because sometimes they're just going to give you a word sentence. They're going to give you the names of the compounds, and then you have to figure out what the formulas are. It's very fun. Then this is just kind of a tip for number 2. If an element occurs in only one compound on both sides of the equation, balance that first. If there's more than one such element, balance metals before nonmetals. Okay, that's a recommendation. That's not a hard and fast rule. Balancing equations, sometimes there's an easy way and there's a very difficult way. And you want to go with the easy way if you can. So start with something that only has is in one thing on each side. If there's oxygen in all of the compounds, don't start with the oxygen. Start with something else. Metals are often a good place to start. But if you start somewhere and you realize, okay, this is ugly, this isn't working, just start over with something else. It's called balancing by inspection. It's kind of a trial and error method. If an element occurs as a free element on either side, balance that last. Because that one, what we'll find is that sometimes when we balance one element, we mess up something that we've already balanced. If we leave a free element to the end, we can change it and it won't mess up anything else. Then if the balanced equation contains fractional coefficients, change those into whole numbers by multiplying the entire equation by an appropriate factor. Last step, really important, check to make sure the equation is balanced. Go back and double check. Okay? It only takes like 30 seconds maybe, but it ensures that you get it right, because it's really easy to make mistakes. And then here, these are important. Do change the coefficients to balance the equation. Do not change the subscripts. You wrote down the formulas for the compounds at the very beginning. If those are correct, you can't change them. Sometimes it's tempting because, well, if I just change the formula, it's all balanced. I don't even have to mess with coefficients. But you can't change what these substances are. So let's do some examples. Write a balanced chemical equation for the reaction between solid copper and solid sulfur to form solid copper 1 sulfide. So the first thing we have to do is write down the formulas for these things. And generally they're written in order left to right, reactants first, then products. And so we see here this 2 form. So that's like the arrow. Everything listed before that goes before the arrow, it's a reactant. So solid copper, well, we need the symbol for copper is Cu, and it's a solid. If they're giving you the states of these substances, then you should write them down. We do not always write state symbols in balanced chemical equations, but if they ask you to, then you have to. And we're going to practice. So copper, solid. Plus, I'm going to give myself a little space there in case I need to write a coefficient. Solid sulfur. Sulfur is S. Is sulfur one of the diatomic elements? Horses need oats for clear brown eyes. No, there was no S in there. So it's just S. And it says that's a solid. To form copper 1 sulfide. Okay, this goes back to Chapter 5. Copper is a metal. This is an ionic compound. We need to look at the ions first before we can write the formula. Copper 1 is Cu+. Copper with a +1 charge. Sulfide has what charge on it? -2. We count back from the right side of the periodic table, 0, -1, -2. So we see these charges are not the same. We'll do that crisscross thing, and we'll end up with Cu2S, and that is also a solid. So there's our first step. We've got our skeletal equation. We've got all the formulas in there, but it's not balanced. So I'm going to show you one method to balance these things. Well, maybe I'll show you that on the next one because this one's awfully simple. Let's just look at this one. How many copper atoms are on the left side? 1. And how many is on the right side? 2. So we need another copper atom on the left side. So if we put a coefficient of 2 in front of that, now we've got 2 coppers. 2 coppers on the left, 2 coppers on the right. How many sulfur atoms on the left side? 1. And how many on the right side? 1. Done. We're balanced. That one was pretty simple. Any questions? Here's another one. Write a balanced equation for the reaction between sulfur dioxide gas and oxygen gas. Again, those words to form sulfur trioxide gas. So sulfur dioxide. What kind of a compound is that? Is it ionic? No. Is it an acid? No. It's one of those binary molecular covalent things with the prefixes, right? Sulfur dioxide means that there's 1 sulfur and 2 oxygens. There we go. Forgot to tell it I wanted to write sulfur dioxide, and it's telling us it's a gas. That's reacting with oxygen gas. Oh, is oxygen a diatomic element? Yes. That's the oats, and horses need oats. So that's O2. When we have those 7 diatomic elements, if we have any one of them by themselves, then we put the 2 on it. If it's in a compound with something else, then we don't think about it being diatomic. And this is going to form sulfur trioxide. What's the formula for sulfur trioxide? SO3. And again, this is a gas. So we've got our formulas in there. And here's another little tip. If you're balancing your equation and you realize there is no possible way I can balance this, check your formulas. If one of the formulas is wrong, it may be impossible to balance the equation. So you're not going to get anywhere till you fix that. So this is one way to keep track of what's going on here. It works for some students, so use it if you like it and ignore it if you don't. So I'm going to, on the left side underneath here, I'm just going to list the different elements I have. So I've got sulfur and I've got oxygen. And I'm going to draw a line at the arrow. That's the middle of the teeter-totter. And I'm trying to balance things on each side of the line. And then I'm going to go through and I'm just going to kind of make a little chart here and add up what I've got. So under SO2, I'm going to put a 1 for sulfur, because there's 1 sulfur and there's 2 oxygens. And here in O2, there are no sulfur atoms and there are 2 oxygens. And over here in SO3, there's 1 sulfur and there's 3 oxygens. And now we can see a little more clearly, perhaps, that on the left side we have 1 sulfur, and on the right side we have 1 sulfur. So that's good. In this one, sulfur is definitely the one you start with because there's oxygen in everything. Then we look at the oxygens, and on the left side we have 2 plus 2, which is 4 oxygens, and over here we have 3, and so that's not balanced. So we need to add more oxygens to the right side. How can we do that? All we can do is make there to be 2 SO3s. So we'll make 2 of these. We can't change that subscript. It'd be nice if we just change it to SO4, but we can't do that because that's not what actually happens. So if we have 2 of these, now these numbers change. Now instead of 1 sulfur, we have 2 sulfurs. Instead of 3 oxygens, we have 6 oxygens. So, well, now we messed up the sulfur. So we better fix the sulfur before we go on and finish the oxygen. So yeah, we got to put a coefficient over here so that we can get another sulfur on the left side. And that's going to change these guys. So this becomes a 2, and now we have 2 times 2 is 4 oxygens. So we have 2 sulfurs on the left, 2 sulfurs on the right. Let's turn our attention back to the oxygens. How many oxygens do we have now on the left side? 6, 4 plus 2. And on the right side we have 6. And so there we go. That's our balanced equation. Any questions? It's one of those things you got to practice. Yes, it does make one sleepy. Write a balanced equation for the reaction between aqueous hydrochloric acid and solid manganese 4 oxide to form aqueous manganese chloride, liquid water, and chlorine gas. Oh, so this is getting a little more complicated. We can do this, okay? We're getting some practice from chapter 5, aren't we? So again, we have this to form or to produce, something like that. That tells you where the arrow goes. So we've got hydrochloric acid and manganese 4 oxide on one side of the arrow, and we've got the other stuff on the right side of the arrow. So hydrochloric acid, what's the formula for that? HCl. Hydrochloric, the hydro prefix tells us it's just hydrogen and one other element. Chloric means it's chlorine. So we've got HCl, and it says it's aqueous, and so we write AQ. And manganese 4 oxide. So manganese is Mn, and that Roman numeral 4 tells us the charge is 4+. Oxide, oxygen forms an ion that is 2-. Now this is one of those unusual ones where we have to be a little careful with the whole crisscross idea. So if we crisscross these, because 4 and 2 are not the same, then we end up with Mn2O4. Hmm? This is manganese oxide.
Oh, first one, sorry.
Yeah, manganese chloride is the second one.
Yes.
Yeah, we'll worry about that one later. So 2 to 4, that's not the lowest ratio. With ionic compounds, we want the lowest ratio. So that's not what we want. Whoops. I'll just start over. 2 to 4 is the same as 1 to 2. So that's one of the rare situations where the crisscross method can get you into trouble. +4 minus 2, we need 2 minus 2's to equal the +4. And it says that's a solid. I did not leave myself even close to enough room. So I'm going to start over because I can. HCl AQ plus MnO2 solid goes to, now we've got manganese 2 chloride, manganese 2+, and chloride forms a -1. So that is MnCl2. And it says that that is aqueous. Liquid water, what's the formula for water? H2O with an L. And chlorine gas. I still ran out of room. Dang it. Cl2. Oh, that's the advantage of the whiteboard, is you can just go on and on and on. Okay, so this is not ideal. Oh, well. Yeah, lovely, thank you. Well, now I have to write it over again. Okay, so there's our skeleton. And sometimes you have to just move over to the next line, but I'm trying to avoid doing that. So here we've got a lot more elements, and so this table is maybe going to be a little more, even more helpful. So I'm going to do the table. I'm going to do a different color this time. Yellow's nice. So I'm going to draw a line here. And then over here I'm going to list out, I've got H, and I have Cl, and I have Mn, and I have O. And I need to keep track of all of these things. So in HCl, I have one H and one Cl, and I have no manganese and no oxygen. In MnO2, I have none of those first ones. I have one manganese, and I have two oxygens. Over on this side, I've got no hydrogens, two chlorines, one manganese, and no oxygens. In water, I have two hydrogens, no chlorines, no manganese, and one oxygen. And over here, 0, 2, 0, 0.
How do we know we have two chlorines?
Oh, good question. How do we know there's two chlorines? Why is it Cl2? Diatomic element. Horses need oats for clear brown eyes. So chlorine as an element by itself is always Cl2. Okay, so a lot of times just starting at the left with the first element seems to work out okay. So hydrogen, is the hydrogen balanced? No. We have two hydrogens on the right side and we only have one on the left side. So we need to put a coefficient of 2 in front of the HCl, and that changes this one, and it changes this one. Hydrogen's balanced. If we do anything to mess up the hydrogen, we'll have to come back and fix it again. Let's do the chlorine. On the left, there's 2 chlorines. On the right, we have 4. So we need more chlorine on the left side, right? So this shouldn't be a 2. That needs to be a 4. Then we have 4 hydrogens and 4 chlorines. Now we messed up the hydrogen. So we need to fix that. We'll have to put a 2 over here. That changes this one, and it changes this one. So we have 4 hydrogens on the left and 4 hydrogens on the right. 4 chlorines on the left, 2 plus 2, 4 chlorines on the right. Manganese, 1 and 1, thank goodness. Oxygen, 2 and 2, phew. Okay, because it looked like it was maybe going to be a little ugly there at the beginning. That's what I mean by kind of going around in circles. I fix, the hydrogen's okay, and then I fix the chlorine, and that causes the hydrogen to change, and then sometimes you'll go around and it's like you're just changing one after the other. If you go around in circles a couple times, then there's something wrong. Start over somewhere else, check your formulas. But there's our balanced equation. Any questions? I think we got one more example here. Balanced equation for the reaction between liquid benzene and gaseous oxygen to form carbon dioxide and liquid water. They're giving us the formula for benzene because that's not something that we've taught you how to name yet. And we won't in this class. So C6H6. And it says that's a liquid. And that's reacting with oxygen. And the formula for oxygen is O2 because it's a gas, it's a diatomic element. And that's a gas. Arrow. Carbon dioxide, CO2. It says that's a gas. Well, it doesn't say, does it? What do we know about carbon dioxide? It's a gas, right? Because we breathe out carbon dioxide. Hopefully if you got through high school, somewhere along the line, someone told you about that. And liquid water. And again, I'm running out of room. I'm going to write it down here. H2O, liquid. So we got our formulas in there. Let's see how it's going to pan out here. Here we've got carbon, hydrogen, and oxygen. In C6H6, we have 6 carbons and 6 hydrogens and no oxygens. Over here, we have no oxygen, no carbons, no hydrogens, and 2 oxygens. Carbon dioxide, 1 oxygen, no hydrogens, and 2 oxygens. And over here, yeah, he's kind of in the way. There's no carbons in him. We've got 2 hydrogens and an oxygen. So in this sort of a problem, you're going to want to leave the oxygen for last because oxygen's all by itself there, O2, as one of the reactants.
Doesn't that have 2 hydrogens, 1 oxygen, not 2 hydrogens, 0 oxygen? Let's see, H2O.
Two hydrogens. Oh, thank you. Yes. Yeah. There we go. That's better. See, we all make mistakes. Let's start at the left. 6 carbons on the left. There's only 1 carbon on the right. So we need to put a coefficient here of 6. And that's going to change all the numbers underneath except the zeros. So this is going to be now 6 carbons and 12 oxygens. You see that? So now we balance the carbons. We have to look at the hydrogens. On the left we have 6 hydrogens. On the right we have 2. We need to multiply that by 3 so that we can get 6 hydrogens, and now we're going to have 3 oxygens. You with me? So carbons are straight, hydrogens are straight, oxygens. On the left side we have 2 oxygens. On the right side, 12 plus 3 is 15. 15 oxygens, but when we look on the left side, the oxygens are coming in pairs. So we have an odd-even issue here. There's 2 ways to solve this problem. One is to use a fraction, and the other is to just double everything. Because when you double an odd number, it becomes even, and the problem goes away. So we can use a fraction. We could put a fraction of 15 halves in front of the oxygen, and then multiply everything by 2. That's the way the book tends to teach it. Students don't generally like that. They don't like fractions. To start with, I have a friend who teaches middle school math, and for her students, fraction is the F word. You know, they just hate fractions.
Sounds like my daughter's teacher. She's
Yeah,
saying that.
fractions are the F word. So I like fractions, but we can avoid them. So we see that we have 15 oxygens here and that they're coming in pairs over here. That's what I call an odd-even problem. There's no getting around it by just adding to the left side, because you can't add half of an oxygen molecule. So let's double all the coefficients, and then we'll be able to fix it. So we're going to put a 2 here, because that was a 1. So now we've got 12 and 12 and still 0. We're going to leave this guy alone, because that's the one we're working on. You could put a 2 there if you want to, but I'm just going to leave him alone. And we're going to double this one to a 12, and we're going to double this 3 to a 6. This 12 means that now we have 12 carbons, and we have 24 oxygens. Don't be afraid of that big number. It's okay. Some of these, especially these combustion reactions, have big numbers. 3 water molecules mean we have 12 hydrogens and 6 oxygens. Now if we look at 24 plus 6, we've got a total of 30 oxygens on the right side. They're coming in pairs on the left side, so we need a coefficient of 15.
If we didn't want to double it, can we put 7.5?
You could put 7.5, but then you're going to have to multiply by 2, because in a properly balanced chemical equation, they all have to be whole numbers. So we can't have fractions or decimals. It's a good question. Any other questions? So a lot of times when you're, balancing an equation, especially when you're first starting out, you're going to make a mess and then write it out neatly. And you're probably going to encounter a few formatting issues with mastering chemistry. I'll just warn you of that in advance.